Hi, my name is Min. And okay, so today I'm gonna show you a tutorial to becoming a arborist. I found this word on dictionary. Well, it's about like professional with working with the trees. Yeah, like bonsai in Japan, something like that. Well, so actually in this tutorial we're working with trees. So these are four topics that we'll be discussing in this tutorial. I think this video is gonna be long, so if you're interested in it, I'm very happy if you're here with me to study about this. Okay, so first we'll go through a bit about the graph theory and some, useful knowledge of it. You don't need to really understand it in very deep level, because I don't really, but yeah, you can try to learn more about these later on. So first, a tree is an undirected, connected, and acyclic. Well, acyclic means there's no cycles within the graph. And from these definitions, we have some very nice properties of a tree, like as shown here. And throughout the tutorial, we're also mostly working with a rooted tree. So we assume that a tree is rooted at node 1. Well, the nodes are indexed from 1 to n for an n vertices trees. However, in the centroid decompositions topic, we're not working with a rooted tree. You'll see why it is when we comes there. Okay, so briefly, I just want to say that trees, they have very nice properties. And indeed, if we just simply apply traversal algorithms like DFS or BFS, then you cannot exploit the structures of the tree. Therefore, the four techniques that I'll show you at the very first slide are somewhat of pre-processing algorithms to make to streamline the speed to answer the queries later on. Okay, so these are some kind of useful things that we'll work with. So firstly, we have a range minimum query problem, RMQ. Well, actually, it can be maximum or it can be sum, whatever. Like a range or interval query on an array. So briefly, if you have an array like this, and then you ask like given the 11 right positions, you have to like find out the minimum, maximum, or sum of that interval. Well, you can do this in linear, but it's not efficient when it comes to a lot of queries. Yeah. So here we'll try to organize the data differently, so therefore we can, sacrifice a bit of memory, but indeed we gain some speed when answering the queries. So here this just broke out the array into a tree of into a segment. They organize it as tree, and at each node they store like minimum, maximum, of sum of that interval. So that's sub interval actually. And these RMQ problems can be approached via a sparse table instead of a segment tree. So in a segment tree here, we will find a middle point and we try to divide it and into a subinterval of half size and working with combinations on that half size subinterval. But in a sparse table, we also broken down an array, but we break down it differently. So in the sparse table, we'll have a start index and a length of this from the start index. So this array will store simply the start index and the length of the sub-array starting from that index. So they're organized differently, and therefore we have to, they will spit up different kind of queries on their own sake. Okay, just briefly about that. So now we've come with the very first algorithm, Euler technique. So, oh, so briefly about Euler tool, we have a graph. So an Euler tool is like, it asks you if you can find a tour that start from a vertex, going through every edges in that graph, and then back to the original vertex that you started. Okay, that's an Euler tool, what it is. And the problem we have here is now, so I want you to find minimum or maximum or the sum of the nodes within a subtree. Well, how can we do that? DFS, BFS, whatever you want. It can be, but again, we are working like there are many queries, the same queries like that, how we make it efficient. So instead, the Euler tool technique, the idea is basically you will try like from an unstructured tree graph, we'll flatten it out in a 1D array, and therefore you can use the segment tree or the sparse table to streamline the answer of the process. So here about this, we just simply like another routine is like combinations of pre-order and post-order traversal. So firstly we visit, we start in the team, which is like a pre-order, and then when we finish and visit all the descendants, we get out of it and we record it in T out. And this is the post order, and we can also have an auxiliary array like an Euler array, so like the order of the visited nodes. So of course you'll see that these nodes are twice, like appear twice in the Euler array, because like when it first start a node, it visit on descendant and it get out, so it will store the first positions and the last positions, the order. Well, the time, like we can have a timer to count the steps when we do the DFS, go with DFS and backtrack. And okay, very interesting, right? Because now you'll find that the subtree, say a vertex B, the subtree of rooted at vertex B will be an interval like this. And then every of its descendants will be exactly within the interval, cannot be up beyond or below that, exactly inside. So now you see that now we have an Euler array like this, and we asking for a subtree, and we know that the subtree is exactly inside the interval. You see, it's back to our initial problem for range minimum query with segment trees and sparse table as the solutions for that. So that's it. So we can solve it in log n by using segment tree and or sparse table, or yeah, and this it depends on whatever the structure you use. Like segment tree or sparse table, they will have quite bit different complexity, and for the for the constructing Euler array, it just requires a DFS, so it's gotta be linear in the number of nodes of the original tree. Okay. Yep, just these are the properties that I told you. Okay, so now we move to the next problem, the LCA. Well, it stands for lowest common ancestor. So basically from the definitions, and it's also our problem. So we have the two vertices. We want to find its deepest node, that is an ancestor post of them. Okay, for example, like this figure you see, like say have 6, 7. Well, we can say that the number 3 is parent of 6, 7, right? Actually, yes. Um, well, it's a parent, or actually it can be an ancestor, right? So, and then number 1 here can be an ancestor, right? We have 1 and 3 are possible ancestors. So, now we can just actually like go just go whatever the ancestors they are, but it's not interesting. We just want to see find the closest ancestor to them. So actually this is 3, but here like I chose 4, 7, so basically this only have 1 as its ancestor. Yeah, but that's it. Our problem is just to find the closest deepest node that is an ancestor of both of the vertices. So you can again you can find it in ON, of course, DMS, but it's not efficient. And we can do it in fact log n to find the LCA of those two vertices. How? Well, there's many ways. We have square root decompositions. We have sparse table with binary lifting, or many more. But here we will try to utilize the algebra we introduced previously and those secondary or sparse table. So similarly, well, in fact, we can transform the problem from LCA into RMQ. But firstly, we'll do the Euler tour, flatten the tree again. Here, we store the first occurrence of each node, and you see in the Euler tour, you will see like between the first, because like because as I said before, like those two nodes, the ancestor must, like here, like the ancestor must be covered two nodes. So basically, if we use the first occurrence of it and the first occurrence of the of a node, then actually at one point the Alator will store some of the the it will go back to the ancestor. So basically we are just like try to flatten it out, and then we will find the node with the deepest in the elder tool. It's just like an range minimum 3 again. Yeah, so in fact we can just turn back to our elder tool problem. Firstly, we can use minimum segment trace and a sparse table. Yep. So okay, so now we move on to another problem called HLT. Oh, well, it stands for heavy light decompositions as a decomposition technique. So use that like heavy light. Is very familiar with that from the AVL tree, right? Yeah, it's quite similar here. So now we'll give a problem. Okay, so previously Eleanor solved a subtree, and now we interested in the path from two nodes and some combinations on that path. Well, LCA and DFS will help, but of course, if you go through on the path to compute, then it must cost you linear, right? Because even though if you use LCA to find the path, it's in log n, right? But for combinations, you have to do heavy nodes on it on the path, so that's probably linear. Okay, we can approach this problem a bit different. So we can try to define the heavy edges and light edges. Well, preferably the heavy edges. Okay, so we start with the heavy and light child. So similar to those in AVL, the heavy child. Okay, so the heavy child will store most of like the subtree root at heavy child will store the largest number of descendants compared to other children of the parent. So theoretically, the heavy child must be somewhat like half size of the parent subtree, but okay, for ease of implementations, we can make it to be the children with the most with the biggest size. So that it doesn't matter. Well, so here you see, as you can see, that these heavy edges, all of them, the consecutive heavy edges will form a what called heavy path. Well, you may find that there can be like a light path, right? Yeah, possibly it can happen, but we're not going to define it because we'll see it as the light edges as the like link between the heavy path. And there we go. So what's interesting about this is that the number of heavy the number of heavy how can I say the number of uh line edges you visit in a path from two vertices is at most log n, and thus the number of the heavy path from between two vertices also log n at most. So why is it? I think you can refer to my article. It's gonna be so long if I explained it to you. I just want to say something at high level for you to understand about this. So so briefly, like you see, as from our definitions, the heavy and light child, then if we go to the light child, it's probably reduced like at most, like nearly like half of the size of subtree, you see, every time we pass a light edge. And same thing for, and since these are log n and the heavy edge also, like if we pass a light edge here, the tree is reduced by a factor of like 2, and then we are left with either a heavy path or not a light edge, then it's obviously only like half size of our original tree. So therefore, it's gonna be at most log n. Well, for more details, read my article. Yes. Okay. So here we just basically do very simple thing. So we just use DFS as usual, but now instead of so what makes it efficient is the way that we can compute the heavy path in log n instead of in linear time, in logarithmic time instead of in linear. Well, to do this, again, you can apply segment tree or sparse table or whatever the data structures that can be done to the conversions in log n. And thus, since you only pass through log n light edges or log heavy path, and you have log n commutations, and therefore you end up to answer very in log n square. Log n whole of square. I mean, log square and something like that. It's not n square. It's log square of the log. Yep. So that's it. And like instead of for each heavy path, we construct like an independent segment tree. There's a way that we can do to construct only a single segment tree that you use for all the heavy paths. Yeah. So refer to my article for more details. Okay, lastly, centroid decompositions. Now we move to another problem. Okay, so previously we do with the, like some local queries like subtree or a path, but now I'm interested in all the global queries in whole tree. A very typical example is count the number of paths subject to some constraint. Specifically here, we want to count the number of paths with exactly k vertices. So again, you'll find it divas. Oh, n square. You want it? No, I don't. So we're gonna have a very interesting decomposition algorithm called centroid decomposition. Well, first I'll tell you about what a centroid is. So there's a very interesting property of a tree is that there's in a tree there's probably at least one and at most two centroids. Well, in a centroid is that when you delete that from the tree are disconnected, but they will form a connected components, right? It will have a forest of trees, and each of which cannot have the size more than half of the original tree before removing that node. That is very interesting. So you have to also note that there's difference between a centroid and a center. A center is like, you find a node that is minimize the maximum distance between it to other nodes in the tree. While centroid is that removing it, it will leave connected components with cannot have more than half size of the original tree. So that's the difference, but we'll only work with a centroid here. So just keep it in mind that they're completely different things. They may intersect some points, but in generally they're different notions. Okay. So the workflow, so it's pretty kind of quite hard to understand, but you have this thing like we have a centroid, right? Firstly, we come with a like how we can find a centroid efficiently. Well, actually, just a normal DFS, no more. I mean, like we can start with any vertex. We can, estimate. I don't know. Actually, we can compute the subtree size around that node, right? And therefore, if we find a node that is more than half size of the current tree, then we move to that node and we count again, and we continue move until there's no like subtrees, no children with the subtree root at them are more than the size of a current tree. It definitely converge because we never get back to the parent, otherwise we terminate there, and we can only move to the one that can, possibly a centroid. Okay, more data proof is provided in the article, but simply That is the correctness of the algorithm. And now when we have a centroid, right, we just simply like remove it. And now we have connected components, and from each of which we can continuously find the centroid of those components and then delete it. And yeah, there we go. So here, back to our figures, you see that the left one is the original tree and the right one is the central decomposition tree. So firstly, we find central tree here, and therefore it's separated into 4 components. Each of which we again find another central of them, and we decompose their subtree, and until there's no vertices in the final tree. So we're done. So, well, how is solve our previous problem? What does counter number path with exactly k vertices? You have to claim a very obvious, you know, fact that for counting number path with exactly k vertices, we have a vertex u, say this number 3. Say if the path with exactly 2 vertices, then it's gonna be 2, 3 or a 3, 1. Whatever the path is, the node 3 must be in that, right? Okay, that's one point. And the second point is that the central decomposition give us is that you see from any 2 vertices in the original tree, its path must go through the centroid in the centroid tree here. Okay, as an example, we have the 9, node 10 here. You see, there's a path 9, 6, 3, 5, 7, 10. It passed these nodes, right? And you see, it passed this node 3. What this node 3 is the centroid. Is a centroid in the centroid tree. You see, 9 here, 10 here. And for LCA, again, can apply that here. LCA with 5, 3 to 10. There we go. What we're gonna do now. So we know that previously a path must pass through a vertex. So simply we can first find a centroid, and then we use multiplications or additions or dynamic programming, whatever you want, to count the number of paths that going through that centroid in the centroid tree, and then remove it, and then you go with those subtrees. And indeed, by doing this, the height of a centroid tree is only log n, and the sum of at each level is asymptotically linear. The sum of the nodes at each level, we don't know, so asymptotically is linear. So in total, is only n log n to process for each of a centroid. So there we go. Instead of n squared, we reduce to n log n. And that is something as quasi-linear. Very efficient, right? Just like sorting out a riddle. So that's it. So to sum up here, we have 4 algorithms. Each of it provide their own set for different problems. They sound related. Indeed, heavy light and centroid, they can use LCA, L-Tour, and LCA use L-Tour. You see, they're all connected, but they serve different purposes. So briefly, again, the L-Tour will compute the subtree. LCA will find the path between 2 nodes efficiently in logarithmic time. Heavy light will do computations of a path in log n, or actually logs n, square of a log n. And central decompositions will deal with the queries on the whole tree. So, well, complexity is proportional to a factor of log n for central decompositions, depending on what computations we do at each centroid. So, yeah, so that's it. I just want to say that these are very nice algorithms. These are just pre-processing steps, and therefore they can streamline your operations later on for repeated actions. And well, you have to, gain insights from that structure first, and then you have to appropriately apply the data structures and algorithms. That is a core of, problem solving things. Detect what a problem is and then solve it with appropriate tool, because there's no free lunch algorithm. Yes. Okay, so to me, I have some really not some list that I think is very good to learn about data structures, algorithms, computer science things, discussions, and forums. Well, these are listed here. These are all English sources except the first one. The first one is specifically for Vietnamese students and readers, but you can use the translations. And indeed, actually, they usually translate the sources from these, but why I recommended this one, because they give a more concise C++ implementations than these. I think so. Yeah, according to my experience. So that's it. Thank you for your listening.